Now, welcome. In my previous lecture, we have studied Hartley's almost unbiased ratio estimator. So, we have seen that the usual ratio estimator and the Hartley's almost unbiased estimator, they can be used depending upon the closeness between R, beta and Rn bar. So in this class we shall study another almost unbiased ratio estimator due to Quenouille. So we shall consider the technique of estimating the bias of a ratio estimator unbiasedly to the second order of approximation. This technique lies in reducing the bias of the ratio estimator from one order to another, because the ratio estimator it is biased up to second order, but this Quenouille estimator, this will be unbiased up to second order of approximation. Now this means we have the usual ratio estimator is biased, and its bias is given by bias in the usual ratio estimator is given by y bar 1 plus 1 minus f by n cx square minus rho cy cx. This is up to order of n inverse. Now, but by this technique, an estimator is obtained which will have no bias of order n to the power minus 1, but has a bias of order n to the power minus 2, and so on. So the proposed estimator is an unbiased one approximately, and we call it almost unbiased ratio estimator. Now these conditions under which the unbiased ratio estimator due to Hartley's will be more efficient than the usual biased ratio estimator were also derived, and these are restrictive, and because they are not realizable in practice, we will therefore consider another method, and this is Quenouille. It is developed in 1956, and it helps to reduce the bias of the ratio estimator. So here we shall take a simple random sample of size 2n. Simple random sample of size 2n, which is splitted at random into two subgroups. Which is splitted at random into two subgroups. Each of size n, and denote by y r bar 1, y r bar 2, and y r bar 3. The usual ratio estimates based upon the two subsamples of size n and the entire sample of size 2n respectively. So we have y r bar 1, that is equal to y1 bar by x1 bar into x bar. Y r bar 2, that is equal to y2 bar by x2 bar into x bar, and y r bar 3, that is equal to yr bar 3 that is equal to y2n bar by x2n bar into x bar. So here yr bar 1 and yr bar 2 based upon the sample of size n, and yr bar 3 is based upon the sample of size 2n. Now we consider the weighted or pooled estimate. YW bar equal to W1 yr bar 1 plus W2 yr bar 2 plus 1 minus W1 minus W2 yr bar 3. So this we consider the weighted estimates. Now since yr bar 1 and yr bar 2 are based upon the same sample size, so we can consider W1 equal to W2, that is equal to W. So this estimator YW bar can be reduced to YW bar equal to W yr bar 1 plus W yr bar 2 plus 1 minus 2W yr bar 3. Now we shall now determine the weight W so that the bias of the estimator YW bar to the first order approximation will be 0. So now consider expectation of YW bar, that is equal to W expectation of yr bar 1 plus W expectation of yr bar 2 plus 1 minus 2W expectation of yr bar 3. So now to the first order of approximation we have expectation of yr bar 1 equal to expectation of yr bar 2, that is equal to y bar whole into 1 plus n minus n by n into 1 by n cx square minus rho cy cx, and expectation of yr bar 3, that is equal to y bar 1 plus n minus 2n by n into 1 by 2n into cx square minus rho cy cx, because it is based upon the sample size of 2n. So now expectation of YW bar, that is equal to 2WY bar 1 plus n minus n by n into 1 by n cx square minus rho cy cx plus 1 minus 2W y bar 1 plus n minus 2n by n into 1 by 2n cx square minus rho cy cx. Now this is equal to y bar plus y bar whole into cx square minus rho cy cx. We can take this common. Now let this will be 2W n minus n by nn plus 1 minus 2W n minus 2n by 2nn. Now so up to order of n inverse, the estimator YW bar will be unbiased for Y bar if this term will be 0. If 2W n minus n by nn plus 1 minus 2W n minus 2n by 2nn, this is equal to 0. This implies we can get W equal to minus n minus 2n by 2n. So putting this value of W in YW bar, we get YW bar equal to this, we have YW bar equal to 1 minus 2W YR bar 3 plus W YR bar 1 plus W YR bar 2. So that is equal to 2 n minus n by n YR bar 3 minus n minus 2n by 2n YR bar 1 minus n minus 2n by 2n YR bar 2. This is approximately equal to 2 YR bar 3 minus 1 by 2 YR bar 1 minus 1 by 2 YR bar 2. Now our estimator is approximately equal to this. So now we have to find its mean square error. Now if we ignore the finite population factors, then YW bar will be equal to this. So expectation of YW bar is equal to Y bar up to first order of approximation, order of n inverse. Thus to the order of n inverse, the usual ratio estimator YR bar is a biased estimator of population mean Y bar, whereas this Quenouille estimator YW bar is unbiased estimator of Y bar. That is why the estimator YW bar is called as almost unbiased ratio estimator of population mean Y bar. Now the mean square error. Now mean square error of YW bar, that is equal to expectation of yw bar minus y bar whole square, that is equal to 2 expectation of y bar 3 minus y bar minus 1 by 2 expectation of y bar 1 minus y bar minus 1 by 2 expectation of y bar 2 minus y bar, this whole square. Now that is equal to 4 into variance of y r bar 3 plus 1 by 4 variance y r bar 1 plus 1 by 4 variance y r bar 2 minus 2 covariance of y r bar 3 y r bar 1 minus 2 covariance of y r bar 3 y r bar 2 plus 1 by 2 covariance of y r bar 1 y r bar 2. Now we have to find these values. Now here variance of y r bar 3 can be obtained by using 2n in place of n for the usual ratio estimator, and this is the variance of the usual ratio estimator. Now we shall find each of the covariance terms here. Now we have variance of y r bar 3, that is equal to n minus 2n by n into 1 by 2n y bar square cy square plus cx square minus 2 rho cy cx, and variance of y r bar 1 equal to also variance of y r bar 2, that is equal to n minus n by n into 1 by n y bar square cy square plus cx square minus 2 rho cy cx. Now to find the covariance terms, we consider y r bar 3 minus y bar, that is equal to y2n bar by x2n bar into x bar minus y bar, that is equal to y2n bar into x bar by x2n bar minus y bar. This implies expectation of y r bar 3 minus y bar, that is equal to expectation of y r bar 3 minus y bar into expectation of x2n bar by x bar. So this is equal to expectation of y2n bar into x bar by x2n bar minus y bar into expectation of x2n bar by x bar. Now, since expectation of x2 n bar equal to capital X bar, so expectation of x2 n bar by x bar will be equal to 1. So this will be, so therefore it is equal to only expectation of y2 n bar minus r x2 n bar. R is y bar by x bar. Because of this expectation of x2 n bar equal to x bar. So this will be equal to 1. So now we find the covariance terms. Now covariance of y r bar 3 y r bar 1. This will be expectation of y2 n bar minus r x2 n bar into y1 bar minus r x1 bar. Now this is equal to expectation of y2 n bar y1 bar minus r expectation of y1 bar x2 n bar minus r expectation of y2 n bar x1 bar plus r square expectation of x1 bar x2 n bar. Now this is equal to expectation of y2 n bar expectation of y2 n bar into expectation of y1 bar given the sample of size 2n minus r expectation of x2 n bar into expectation of y1 bar given sample size of 2n minus r expectation of y2 n bar into expectation of x1 bar given sample size of 2n plus r square expectation of this is x1 bar into now expectation of x2 n bar do expectation of x1 bar given sample size 2. Now this is equal to expectation of y2 n bar into y2 n bar because this is y1 bar expectation of y1 bar given sample of size 2n this will be y2n bar, because this 2n sample size is splitted into the sample size, two subsamples of each of size n, and y1 bar is the mean for the this one of the sample. So minus r expectation of x2n bar, this will be also y2n bar, minus r expectation of y2n bar into x2n bar, plus r square expectation of this is x2n bar and this is x2n bar. Now this is equal to expectation of y2n bar square minus 2r expectation of x2n bar y2n bar plus r square expectation of x2n bar square. Now this is equal to variance of y2n bar square minus 2r covariance of x2n bar and y2n bar plus r square variance of x2n bar. This is a variance of y2n bar. Now this is equal to n minus 2n by n into 1 by 2n. This is y square minus 2r syx plus r square sx square. Now this is covariance of yr bar 3 and yr bar 1. So now for other covariance terms, covariance of yr bar 1, yr bar 2, that is equal to expectation of y1 bar minus r x1 bar into y2 bar minus r x2 bar. This is equal to expectation of y1 bar y2 bar minus r expectation of y2 bar x1 bar minus r expectation of y1 bar x2 bar plus r square expectation of x1 bar x2 bar. Now this is now expectation of y1 bar and y2 bar. This is equal to, here now we can see that x2n bar, this is based upon a sample of size 2n. So this is x2n bar equal to x1 bar plus x2 bar divided by 2. Similarly, y2n bar equal to y1 bar plus y2 bar divided by 2. That implies y1 bar equal to 2 y2n bar minus y2 bar. Now using this result here, this will be equal to expectation of this is 2 y2n bar minus y2 bar into y2 bar. So that is equal to expectation of 2 expectation of y2n bar y2 bar minus expectation of y2 bar square. Now this is equal to 2 expectation of y2n bar to expectation of y2 bar given 2n minus expectation of y2 bar square. This is we have variance of y2 bar equal to expectation of y2 bar square minus expectation of y2 bar whole square. So that is equal to expectation of y2 bar square minus y bar square. So expectation of y2 bar square will be equal to variance of y2 bar plus y bar square. So this will be equal to variance of y2 bar plus y bar square. Now this is equal to 2 expectation of y2n bar. Expectation of y2 bar given 2n, this will be also y2n. So this will be 2 expectation of y2n bar square minus variance of y2 bar minus y bar square. Now this will be equal to 2, this is variance of y2n bar plus y bar square minus variance of y2 bar minus y bar square. So this will be 2 variance of y2n bar plus 2 y bar square minus variance of y2 bar minus y bar square. So this will be now equal to 2 variance of y2n bar minus variance of y2 bar plus y bar square. So this is equal to, this is 2 n minus 2n by n into 1 by 2n. This will be sy square minus because this is based upon the sample of size n, sample of size 2n selected by SRSWOR scheme. So this will be n minus n by n into 1 by n sy square plus y bar square. Now this will be equal to n minus on simplification we can get this is minus 1 by n y bar square into cy square plus y bar square, where cy square equal to sy square by y bar square. So similarly, expectation of x1 bar x2 bar, that is equal to minus 1 by n x bar square cx square plus x bar square, where cx square equal to sx square by x bar square. Now again we have to find out expectation of x1 bar y2 bar. Now proceeding in the similar way, we can get this is equal to minus 1 by n y bar x bar rho cy cx plus y bar x bar, that is also equal to expectation of y1 bar x2 bar. Now using these we can get covariance of y r bar 1 and y r bar 2, that is equal to minus 1 by n y bar square cy square plus cx square minus 2 rho cy cx. Now using all these values we can get the mean square error of yw bar or variance of yw bar, that is equal to for variance of y r bar 3 plus 1 by 4 variance of y r bar 1 plus 1 by 4 variance of y r bar 2 minus 2 covariance of y r bar 3 y r bar 1 minus 2 covariance of y r bar 3 y r bar 2 plus 1 by 2 covariance of y r bar 1 y r bar 2. So this will be equal to 4 n minus 2n by n 1 by 2n y bar square theta plus 1 by 4 n minus n by n into 1 by square y bar square theta plus 1 by 4 n minus n by n into 1 by n y bar square theta minus 2 n minus 2n by n 1 by 2n y bar square theta. So where theta we take cy square plus cx square minus 2 rho cy cx. Now on simplification we can get mean square error equal to 1 by 2 n minus n by n into 1 by n y bar square theta minus 1 by n y bar square theta, that is equal to n minus 2n by n into 1 by 2n y bar square theta, that is equal to variance of y r bar 3. Now from this expression we have seen that the mean square error of the estimator yw bar due to Quenouille is same as the variance of the ratio estimator based upon the sample of size 2n. So from this expression we have seen that from a given sample of size 2n we can find two different estimators for y bar. One is the usual ratio estimator, that is y r bar 3, and other second is the yw bar due to Quenouille. So now the usual ratio estimator y r bar 3 is a biased estimator to the order of n inverse. To the same order of approximation, Quenouille's estimator yw bar is unbiased estimator for y bar, and the large sample variances of both the estimators are equal. Therefore Quenouille's estimator is preferred as it is almost unbiased ratio estimator. Now this is here from the sample of size 2n we split at random into two samples each of size n. So this process can also be generalized to define Quenouille's almost unbiased ratio estimator for the general case also. Now here we shall consider the Quenouille's almost unbiased ratio estimator general case. Now here we have a random sample of size n which is splitted at random into G groups. each having m units, so that n equal to m into g. Now estimates based upon this approach has been suggested by several authors. Ignoring the finite population correction for the moments, the bias of the ratio estimators like r cap is a ratio estimator based upon the sample size n may be expanded in a series of the form expectation of r cap that is equal to r plus b1 by n plus b2 by n square plus up to so on. This is equal to r plus b1 by mg plus b2 by m square g square plus up to so on. That implies expectation of gr cap that is equal to gr plus b1 by m plus b2 by m g square plus up to so on. Now let rj cap is the usual ratio estimator obtained by omitting the jth group. So rj cap is calculated from g minus 1 groups, that is rj cap is obtained from a simple random sample of m into g minus 1 units. So expectation of rj cap equal to yj bar dash by x j bar dash. So expectation of rj cap equal to r plus b1 by m into g minus 1 plus b2 by m square g minus 1 square plus up to so on. This implies expectation of g minus 1 r cap equal to g minus 1 r plus rj cap b1 by m plus b2 by m into g minus 1 square plus up to so on. Now by subtracting we can see expectation of g r cap minus g minus 1 rj cap. This will be equal to r plus b2 by m square 1 by g minus 1 by g minus 1 plus up to so on. That implies expectation of gr cap minus g1 cap rj cap. This is equal to r minus b2 by m square g into g minus 1. by neglecting the higher terms. So this is equal to R minus G by G minus 1 B2 by N square. So up to order N inverse, expectation of G R cap minus G minus 1 Rj cap equal to R. So that is G R cap minus G minus 1 Rj cap is almost unbiased estimator of R up to order N inverse. Now we can construct G such estimators like G R cap minus G minus 1 R1 cap, G R cap minus G minus 1 R2 cap up to so on, G R cap minus G minus 1 Rj cap and G R cap minus G minus 1 Rg cap. Now from these we can consider the Quenouille estimator for the population ratio R is RQ cap equal to G R cap minus G minus 1 by G summation J equal to 1 to G Rj cap. So this is the average of all these estimators. So that expectation of RQ cap equal to R up to order of N inverse. So up to order N inverse, the Quenouille estimator RQ cap is an unbiased estimator of the population ratio R. So when G equal to 2, that we consider as a special case before this. Some other almost unbiased estimators was considered by TIN. This is YT bar equal to YR bar 1 minus F by N Sx square by x bar square minus Syx by y bar x bar. And also BL YB bar equal to YR bar 1 minus F by N Syx by y bar x bar divided by 1 minus F by N Sx square by x bar square. So we can see that variance of the Steen's estimator, variance of the Beal's estimator and variance of the usual ratio estimator are same to the order of N inverse, and this Beal's estimator usually preferred because it cannot take negative values. Now, thank you.